Separating fact from internet fiction and innuendo. According to anonymous Wikipedia intent critics, the ReGenX generator is basically just a hysteresis brake, which requires magnetically saturated cores, in order to function and release the hysteresis drag, while delivering no electrical output power to the load, and the coils must be shorted out, while simultaneously releasing hysteresis drag on the prime mover, due to generator core on load core saturation, thus allowing the system to accelerate under load. Wikipedia criticism 1, hysteresis brake theory 2, core saturation theory 3, no electrical output theory. Anonymous critics of the system have pointed out that the system described by Hines simply demonstrates a change in the motor's hysteresis drag, increasing the speed of the rotor, but not producing any energy. In other words, when the rotor exhibits acceleration following a specific electrical short-out, the device is merely more efficiently converting input electricity to mechanical energy than in the other test configurations. The internet hysteresis brake theory can be immediately dismissed for 3 reasons. 1. Electrical output power. The ReGenX generator and Bi-toroid transformer both deliver more usable electrical output power over their conventional counterparts under identical operating conditions, and are not shorted out. The ReGenX generator delivers 15% more usable electrical output power than the conventional generator coil. See data in Table 1 and 2. The Bi-toroid transformer delivers 69.3% more usable output power than conventional transformer. See all data tables. 2. Core saturation required to produce on-load system acceleration. The ReGenX generator and Bi-toroid transformer both operate below the current magnitude, 341A, required to produce core saturation. See data and oscilloscope current sine waves. 3. Hysteresis brake. The ReGenX generator and Bi-toroid transformer both employs highly efficient amorphous metal, metglas, cores with very low coercivity and low eddy current losses, the exact opposite material, Alnico alloy, used in eddy current brakes. 3. ReGenX generator delivers no electrical output power theory. The false premise presented on the internet is that when ReGenX coils are shorted out, and do not deliver any electrical output power, the cores become saturated with magnetic flux, and this somehow releases the mechanical hysteresis drag on the prime mover, thus allowing acceleration to occur. The key element here is that no electrical power is delivered to the load. This report and the third-party validation test data contained within, clearly shows that the ReGenX generator coils are never shorted out, the coils' cores are never saturated, and that they always do deliver usable electrical output power to the loads, and in fact, the ReGenX generator coils deliver more electrical output power than the conventional generator coils and conventional transformer under identical operating conditions, and they do so, while accelerating the system. 2. ReGenX generator hysteresis brake theory core saturation theory. In order for the Wikipedia internet argument to be correct, the ReGenX generator and Bi-toroid transformer must all operate with saturated cores. The photo data to the right demonstrates a ReGenX generator coil core with 255 amps of electrical current being delivered to it. The oscilloscope shows the coil's current sine wave, yellow, and voltage sine wave, blue. Core saturation is not evident, because the current sine wave is not distorted. The photo data to the right demonstrates a ReGenX generator coil core, which is saturated. 341 amps of electrical current is required to saturate the ReGenX generator and Bi-toroid transformer cores. The oscilloscope shows the coil's distorted current sine wave, yellow, and voltage sine wave, blue. Core saturation is evident, because the current sine wave is clearly distorted. In order to saturate the ReGenX generator and Bi-toroid transformer metglas cores, a minimum of 341 amps of electrical current is required. As flux density approaches saturation, the magnetic current waveform becomes distorted. Metglas is employed as the core material, because it has very low hysteresis, almost zero flux value, and because it is designed to operate well at 400 Hz. Metglas core material makes very poor hysteresis brakes. All of the ReGenX and Bi-toroid transformer prototypes were carefully and professionally designed to operate with coils currents acceptable range, which are always below 341 amps. Prototype number 1 operates with core current in the 1 amp range. 4 amps below core saturation. Prototype number 2. Transformer operates with core current in the 0-2 amp range, and generator in the 1-3 amp range. 2A and 1A below core saturation respectively. Prototype number 3 operates with core current in the 2 amp range. 1.4A below saturation. Core saturation has never an issue in the ReGenX generator or Bi-toroid transformer, and certainly not the prime operating principle, and it could not be hidden. It would be obvious, and self-evident to anyone, as displayed on the oscilloscope sine wave photo data with distorted current sine waves. The first photo data to the right shows the ReGenX coil's current before it enters the conventional transformer. The second photo data shows the current in the conventional transformer primary and the current sine wave for the ReGenX generator coil. Both current magnitudes are well below the required 341 amps, and no core saturation is evident. Note: current magnitudes never exceed 341 amps, therefore no core saturation occurs, which is also clearly demonstrated on the oscilloscope, since the current sine waves are never distorted. Internet fiction: the ReGenX generator does not deliver any usable electrical output power, and relies on core saturation to release hysteresis drag, thus allowing the prime mover to accelerate. Technology fact: the ReGenX generator and Bi-toroid transformer both deliver more usable electrical output power over the conventional generator and transformer under identical operating conditions. The ReGenX generator uses the load current delay to reverse generator armature reaction and accelerate the system under load and not core saturation in its operation. The ReGenX generator is a permanent magnet generator, PMG, and is not scalable, and is not practical as an electric field excited generator. General Electric has demonstrated that 6MW PMG design are perfectly feasible. Potential difference Inc. Designed, built and tested a ReGenX generator, using a DC field excited rotor from a car alternator in 2015. Our tests showed that the DC field excited generator was superior in performance to the permanent magnet rotor design, because the rotor field could be adjusted, increased or decreased, to accommodate load demands. Since 2008, Potential Difference Inc. has developed 5 innovations, which are all based on the load current delay discovery. 1. Patent pending electric vehicle regenerative acceleration. 2. Patent pending ReGenX generator for electric power generation. 3. Patent pending Bi-toroid transformer, BIT, load isolation for power generation transformer. 4. Patented Bi-toroid step-down transformer, BIT, load isolation for power consumption reduction. 5. Patent pending ReGenX stepper motor for EV regenerative acceleration. Conclusions. 1. The ReGenX generator and Bi-toroid transformer both do deliver usable electric output power. 2. The generator and Bi-toroid transformer innovations do not rely on core saturation to relieve hysteresis drag in order to provide system acceleration under load. 3. No core saturation is evident anywhere, and magnetic field strength, Gauss, readings are not required, since core saturation can be observed on the oscilloscope load current sine waves. 4. The ReGenX generator works perfectly as a permanent magnet generator and even better as a field-excited generator. 5. PDI does not manipulate demonstration data nor provides controlled and misleading information and test data. 6. PDI does rely on and continually request outside input in order to improve the innovations and the demonstrations. Clarification of the term infinite efficiency. Infinite efficiency does not mean infinite power. Infinite efficiency simply means that the prime mover input does not need to be increased in order to deliver additional mechanical drive shaft input power, when the ReGenX generator is placed on load. Infinite efficiency does not mean that there are no losses in the system. Core losses, bearing losses, winding losses all still exist, just like any conventional generator. Infinite energy conversion efficiency simply means that there is no generator armature reaction created by the magnetic fields around the current-bearing wires inside the generator, and no counter-electromagnetic torque is produced, and no mechanical input power increase is required, when the ReGenX generator is placed on load. Electromagnetic brakes, also called electromechanical brakes or M-brakes, slow or stop motion using electromagnetic force to apply mechanical resistance, friction. The original name was electromechanical brakes, but over the years the name changes to electromagnetic brakes, referring to their actuation method. Since becoming popular in the mid-20th century, especially in trains and trams, the variety of applications and brake designs has increased dramatically, but the basic operation remains the same. Both electromagnetic brakes and eddy current brakes use electromagnetic force, but electromagnetic brakes ultimately depend on friction and eddy current brakes use magnetic force directly. A hysteresis drag, that may be made from an Alnico alloy, passing through the load. The hysteresis disc is attached to the brake shaft. A magnetic drag on the hysteresis disc allows for a constant drag, or eventually stoppage of the output shaft. When electricity is removed from the brake, the hysteresis disc is free to turn, and no relative force is transmitted between either member. Therefore, the only torque seen between the input and the output is bearing drag. Alnico is an acronym referring to a family of iron alloys, which in addition to iron are composed primarily of aluminium, Al, nickel, Ni, and cobalt, Co, hence Alnico. They also include copper, and sometimes titanium. Alnico alloys are ferromagnetic, with a high coercivity, resistance to loss of magnetism, and are used to make permanent magnets. Properties. Assortment of Alnico magnets in 1956. Alnico 5, developed during World War II, led to a new generation of compact permanent magnet motors and loudspeakers. Alnico 5 magnet used in a magnetron tube in an early microwave oven. About 3 in, 8 cm, long. Alnico alloys can be magnetized to produce strong magnetic fields, and have a high coercivity, resistance to demagnetization, thus making strong permanent magnets. Of the more commonly available magnets, only rare earth magnets, such as neodymium and samarium cobalt are stronger. Alnico magnets produce magnetic field strength at their poles as high as 1500 Gausses, 0.15 teslas. Alnico remnants, B, may exceed 12,000 G, 1, 2T, its coercivity, H, can be up to 1000 Ersteds, 80 Ka/m, its energy product, BH, can be up to 5 mGoe, 44 Ta/m. This means that Alnico can produce a strong magnetic flux in closed magnetic circuits, but has relatively small resistance against demagnetization. Amorphous metal transformer. An amorphous metal transformer, AMT, is a type of energy-efficient transformer found on electric grids. The magnetic core of this transformer is made with a ferromagnetic amorphous metal. The typical material, metglas, is an alloy of iron with boron, silicon, and phosphorus in the form of thin, E25 Guaranese M, foils. These materials have high magnetic susceptibility, very low coercivity and high electrical resistance. The high resistance and thin foils lead to low losses by eddy currents, when subjected to alternating magnetic fields. On the downside, amorphous alloys have a lower saturation induction, and often a higher magnetostriction, compared to conventional crystalline iron silicon electrical steel. Core loss and copper loss. In a transformer, the no-load loss is dominated by the core loss. With an amorphous core, this can be 70–80% lower than with traditional crystalline materials. The loss under heavy load is dominated by the resistance of the copper windings, and thus called copper loss. Here the lower saturation magnetization of amorphous cores tends to result in a lower efficiency at full load. Using more copper and core material, it is possible to compensate for this. So high-efficiency AMTs can be more efficient at low and high load, though at a larger size. The more expensive amorphous core material, the more difficult handling, and the need for more copper windings makes AMT more expensive than traditional transformer. Applications. The main application of AMTs are the grid distribution transformers rated at about 51,000 kVA. These transformers typically run 24 hours a day, and at a low load factor, average load divided by normal load. The no-load loss of these transformers makes up a significant part of the loss of the whole distribution net. Amorphous iron is also used in specialized electric motors, that operate at high frequencies of perhaps 350 Hz or more. Metglas. Metglas is a thin amorphous metal alloy ribbon produced by using rapid solidification process of approximately 1 million C/S, 1800000 F/S, 1 million K/S. This rapid solidification creates unique ferromagnetic properties that allows the ribbon to be magnetized and demagnetized quickly and effectively with very low core losses of approximately 5 MW/kg at 60 Hz, and a maximum relative permeability of approximately 1 million. History. Metglas is based on technology developed at Allied Signal Research Facilities in Morristown, New Jersey, and Vacuum Chemieis in Hanau, Germany. The development of amorphous metals began in 1970. Over the years, many new alloys have been found, using the same principles of rapid solidification. Metglas, also known as metallic glass alloys, differ from traditional metals in that they have non-crystalline structure, and possess unique physical and magnetic properties, that combine high permeability, strength and hardness with flexibility and toughness. Properties. The alloy of boron, silicon, phosphorus, and other glass formers with magnetic metals, iron, cobalt, nickel, have high magnetic susceptibility, with low coercivity and high electrical resistance. Usually the conductivity of a metallic glass is of the same low order of magnitude, as of a molten metal just above the melting point. The high resistance leads to low losses by eddy currents, when subjected to alternating magnetic fields, a property useful for example transformer magnetic cores. The low coercivity also contributes to low loss. Applications. Currently the most important application is due to the special magnetic properties of some ferromagnetic metallic glasses. The low magnetization loss is used in high-efficiency transformers, amorphous metal transformer, at line frequency, and some higher frequency transformers. Amorphous steel is a very brittle material, which makes it difficult to punch into motor laminations. More than ever, electric utilities and industries today are searching for technologies that will reduce their operating costs and improve energy savings throughout their systems. New transmission and distribution, T&D, technologies are now available to help utilities meet these goals. With Metglas amorphous metal distribution transformer, AMDT, with up to 70% lower core loss than conventional transformers, Metglas, Inc. is helping utilities worldwide to achieve their efficiency objectives. When you consider that 10% of all electricity generated by utilities is lost in the transmission and distribution process, the potential savings through reduction in core loss be significant. Ultra-efficient transformer cores made with Metglas amorphous metal alloy make lower core losses possible. Amorphous metal distribution transformers are key to improving utility economics and enhancing energy conservation efforts worldwide. METGLAS 260 SHB1M and 260 SSA1 alloy. Material, iron-based, extremely low core loss. Applications. Distribution, commercial and industrial transformers. Motors. High-frequency inductors. Current transformers. Devices requiring high permeability and low loss at low frequencies. Benefits. Extremely low core loss. 35% of the core loss AF grade M3 electrical steel, core loss at 50 Hz is approximately 70% of 60 Hz values. This is for finished cores. High permeability.